Welcome to this explainer. Today, we're unpacking the absolutely fascinating world of electrostatics. We're going to synthesize the foundational concepts of electric charges and fields, taking a journey that scales all the way from the microscopic realm of subatomic particles right up to massive, infinite planes of charge. And we're doing it with a bottom-up approach to make these complex physical realities completely logical and, honestly, pretty easy to grasp. Let's dive in.
Here is our roadmap for today. We'll start with the basics of electric charge, then move into Coulomb's law and superposition. After that, we'll hit electric fields and dipoles, check out charge distributions and flux, and finally wrap up with Gauss's law and its applications.
All right, Section 1, Basics of Electric Charge.
So, let's start zoomed all the way in. Quantization of charge tells us that charge isn't some continuous fluid you can just pour out in any random amount. Instead, it comes in exact, indivisible steps, these discrete integral packets. The formula here, Q equals plus or minus NE, perfectly captures this reality, with E as the elementary charge of an electron or proton, and N being an integer. You absolutely cannot have, say, half of an electron's charge. It's a fundamental stairstep of nature, no in-betweens.
Now, what about conservation? Well, it means charges can be transferred, but they are never created or destroyed. Think about rubbing a glass rod with a piece of silk. You aren't magically creating new electrical charges out of thin air. You're simply moving existing electrons from the glass onto the silk. The glass becomes positive, the silk becomes negative, sure, but if you add them both together, the total net charge of that isolated system is still exactly zero.
It's kind of fascinating to contrast charge with a concept you already know really well, mass. Einstein's relativity tells us a body's inertial mass actually increases with its velocity, right? But electric charge, it's relativistically invariant. That means an electron's charge literally never changes, no matter how incredibly fast it travels. Plus, while mass only ever exerts an attractive force, charge, depending on its polarity, can either attract or violently repel.
Okay, Section 2, Coulomb's law and superposition.
This brings us to Coulomb's law, the rule that defines the electrostatic force between two stationary point charges. The force, F, is directly proportional to the product of the charges, Q1 and Q2. But take a look at that denominator, R squared. That gives us an inverse square law. The physical meaning here is absolutely crucial. The force drops off incredibly fast as the distance between the two charges increases. If you just double the distance, the force becomes only 1/4 as strong.
So what if we have 3 charges? Or, 10? That's where the superposition principle steps in. Imagine adding a third charge to our mix. The interaction between the first 2 charges is completely unaffected by the presence of that third one. The forces don't interfere with each other at all. They just stack up geometrically as vectors. To find the net force on any one charge, you simply calculate the individual force from every other charge in isolation and then add up the whole shebang as vectors. Easy, right?
Moving right along, Section 3, Electric Fields and Dipoles. We map this invisible aura around charges using electric field lines. Imagine being a tiny positive test charge trying to navigate these strict topological rules. You'd be pushed away from positive source charges and pulled straight towards negative ones. But focus on that fourth property for a second. Field lines never cross each other. Why? Well, because the tangent to a line tells you the exact direction of the force. If 2 lines crossed, it would mean the electric field has 2 different directions at the exact same point in space, and that is physically impossible. Now let's look at a very specific, foundational setup, the electric dipole. It's really just 2 equal and opposite charges, a plus Q and a minus Q, sitting a small distance apart, which we call 2A. This structure is essential for understanding how molecules behave in electric fields. Notice the dipole moment vector labeled P. By convention, this vector always points from the negative charge to the positive charge, acting almost like a little compass needle for the dipole's orientation.
Let's translate this dipole math into reality and see how its field reaches into space. Whether you measure along the axis of the dipole or along its equator, the electric field E is proportional to 1/r cubed. Compare that to the single point charge from Coulomb's law, which we just saw was 1/r squared. The dipole field drops off significantly faster. Why is that? Because from far away, the positive and negative charges practically sit on top of each other and cancel each other's fields out.
Section 4, Charge Distributions and Flux.
All right, I want you to ponder a real physical challenge here. How in the world do we calculate the field for a billion interacting charges? If we try to use Coulomb's law and the superposition principle, we'd have to calculate and add up a billion individual vectors. That is a computational and mathematical nightmare that would take literal lifetimes to solve. There has to be a better way.
And here is the brilliant solution. Instead of counting individual microscopic charges, we smear them out mathematically into continuous densities. Just like you wouldn't count individual fat molecules when spreading butter over your morning toast, we use linear density for a wire, surface density for a flat sheet, and volume density for a solid sphere. We just treat the charge as a smooth, continuous spread over the geometry of the object.
To work with these massive charge distributions, we need a brand new concept, electric flux, represented by the Greek letter phi. Now, let's be clear, flux isn't some physical liquid flowing through a hoop. Actually, scratch that. It's more like a mathematical measure of how strongly the electric field pierces a specific given area. The formula shows that it depends on three things: the strength of the field E, the size of the area, and, crucially, the angle at which those field lines hit the surface.
And that brings us to Section 5, Gauss's Law and Applications. Gauss's law gives us a beautifully simple, elegant equation. Flux equals the enclosed charge divided by the constant epsilon naught. What this means in practice is astonishing, a real game changer. If you draw an imaginary closed surface, think of a 3D bubble around a bunch of charges, you only ever need to care about the net charge trapped inside that bubble to know the total electric field escaping it. You don't need to do a billion vector additions, you just look at the enclosed charge.
Let's see how this builds into a real application. Imagine we have an infinitely long wire of continuous charge. To find its field, we just wrap an imaginary cylindrical Gaussian surface right around it. Gauss's law magically simplifies the math. Because of the cylinder's perfect symmetry, we find that the electric field for an infinite line drops off steadily, exactly as 1 over r.
Now, what about infinite plane sheets? If we apply Gauss's law to a flat sheet of charge, we discover something amazing. It creates a uniform electric field that doesn't weaken with distance at all. None. When you place two oppositely charged sheets parallel to each other, their fields combine perfectly. This uniform non-weakening field is the foundational secret behind how capacitors store energy in all our modern electronic circuits.
So here's the big aha moment, uniting our entire exploration today. Look at how the geometry of the charge completely dictates how far its electric field can reach into space. A tiny dipole drops off incredibly fast at 1 over r cubed. A single point charge reaches a bit further at 1 over r squared. A line stretches it out to 1 over r. And an infinite plane sheet, its field is perfectly uniform, independent of distance entirely. The shape of the matter literally shapes the invisible physics of the space around it. How cool is that?
I want to leave you with a provocative, real-world puzzle. When a metal car is struck by millions of volts of lightning, the electric field inside the cabin is exactly 0. The passengers are perfectly safe because the metal acts as a conductor in electrostatic equilibrium. The excess charge repels itself perfectly, residing entirely on the outer surface of the car. But here's the question to chew on. If Gauss's law dictates that the charge resides entirely on the outside, what happens if that surface shape isn't a smooth car, but has sharp, pointed edges? Keep asking questions and keep exploring.